Okay, so here we are with Unit 8, and we're going to be looking at lesson number 6, and we're going to be looking at equilibrium. So before we do anything else, let's just quickly run through the term equilibrium. It's definitely an important term. So if you look up here, I know this is off a little bit, but we can break it down into two parts. The equal part, and then the R, which stands for rates. So the term equilibrium means that rates are equal, and you'll see what we mean by that. Now, it says when you're looking at the next paragraph, it's talking about something which is actually meaning reversible reactions. And we kind of talked about this earlier, that many chemical reactions, not all, but some chemical reactions and also physical changes can be reversible. And in this particular case, we're really talking about, for the most part, chemical reactions, but you'll see when we look at physical equilibrium that it also refers to physical changes. And let's look at exactly what equilibrium means. And this is definitely a term, a definition that you should know right here. When we refer to a reaction as being at equilibrium, or anything being at equilibrium, that means that the rate of the forward reaction, which means you're looking at the reaction from left to right, is equal to the rate of the reverse reaction, which is going from right to left. That is something that is at equilibrium. And we indicate it using a reversible reaction is indicated using a double arrow. And if the arrows are the same length, it means that it's at equilibrium. And it's what it's explaining down here. Here's the double arrow that you see. Sometimes you'll see an arrow that looks like this. That's the same thing as that. On the Regents exam, I'm pretty sure I've never remember seeing this one. Some dittos you might see that, but on the Regents exam, that's the double arrow that they talk about. A couple of things that you should be aware of. One of the things that always trips students up is when you look at something of reactions that's at equilibrium, it kind of confuses them as to what is actually at equilibrium, what's equal. Well, if you have to remember that at equilibrium the rates are equal, but the concentrations are not equal. The concentrations are constant. Okay, so a reaction that's at equilibrium means that the forward and the reverse reactions are at the same speed, they're equal, but the concentrations of the substances, the reactants and products, are not equal, but they're constant, meaning they don't change, but they don't have to be the same. And that's what this is talking about here. Now these two things here we're not going to go over. This is just kind of redoing what we just talked about up here, but these do have to be done as part of your notes. So it's kind of just going through what was above that. Alright, so let's look at the different types of equilibrium. And on the Regents exam, for the most part, the equilibrium that they talk about is the chemical equilibrium, but there are other types of equilibriums. There's phase equilibrium, there's solution equilibrium, which is from Unit 7, because it has to do with, of course, solutions, and then chemical equilibrium, which is what this unit is about. Let's first look at what we mean by phase equilibrium. And I think the easiest thing to do that, or the easiest way to do that, is to draw a diagram. Wow, that's a bad diagram. Let's say that that's an Erlenmeyer flask, and in that flask we put a little bit of water and we close it up. So we put a stopper. So that's what a closed system is, right? What's going to happen is eventually some of these water molecules are going to evaporate. So you can have some of these water molecules leaving the liquid and changing into water vapor. Eventually this area above is going to become saturated with water molecules, meaning it literally cannot hold any more water molecules. Now, does that mean that the water stops evaporating? You might think it does, but it doesn't. So just because this area reaches saturation of water molecules doesn't mean that the evaporation stops. What happens then once it reaches saturation is that when the next water molecule evaporates, one molecule that's already in the gas phase has to condense. So once this area above the liquid has become saturated with water molecules, the evaporation does not stop. What happens is that for every one molecule that wants to evaporate, one has to condense to kind of make room. And it's kind of like if sometimes if you go into a club and club is full, they don't let anybody in until somebody comes out. So that's basically kind of the same thing. And it can happen with water that is evaporating or condensing, and that would be at a high temperature, 100 degrees. It can also happen with freezing and melting. So if you take a beaker with water in it, and you put a bunch of ice, eventually that water is going to reach 0 degrees. And you would think that once it reaches 0, that ice would stop melting, but it doesn't. So every time one water molecule in the solid phase tries to go into the liquid phase, one molecule that's already in liquid phase goes back into the solid phase. And that develops also an equilibrium. In a solution equilibrium, that happens at what we call a saturation point, when the solvent is saturated. In other words, it cannot hold any more solute. Here's an example. Here's water, and I'm going to dissolve some, in this case, NaCl in that water. Eventually, depending on the temperature of that water, the water is going to become saturated with NaCl, which means that when I put more NaCl, it's going to sink to the bottom. Actually, what's happening is what I put in is not actually sinking to the bottom. Once this liquid, the solvent, the water, reaches saturation point, meaning it can't hold any more NaCl, when I add more NaCl, let's say I add a gram extra of NaCl, that gram that I add will dissolve, but a gram that's already in the solution will settle to the bottom, will precipitate out. And that's what an equilibrium develops. So every time some dissolves, some will crystallize. Chemical equilibrium is exactly what we just talked about. Don't worry about this diagram here. And that's when the rate of the forward reaction equals the rate of the reverse reaction. You don't really need to worry about that. This here. And that's sort of the introduction to equilibrium.